It's a mobility database system on top of PostgreSQL. So during the tutorial, we will explain how to query, how to use the API of MobilityDB in SQL, and general background about how mobility data looks like, how it is represented in the database by this extension MobilityDB. And you will try yourselves the queries with us during the tutorial. Please, anytime you feel to ask questions, just put them in the chat, and we will respond to them as much as we can. So MobilityDB, in simple words, it's an extension of PostgreSQL and PostGIS. So PostgreSQL provides support for the numeric and text data types, for arrays, for range data, also for some advanced types like XML, JSON, or binary JSON. And because it is extensible, a great feature, there is the PostGIS extension that basically provides digital map data management in the database through two main abstractions, the geometry and the geography types. And in the same line, we have built MobilityDB as an extension to both PostgreSQL and PostGIS. And the unique feature of MobilityDB is that it adds the time dimension. So now it's not only about maps, it's about objects that move over map that will change their time, their location with time. So MobilityDB basically provides types for temporal geometry point, temporal geography point, and then in order to be able to describe the time-changing properties of moving objects, there is also temporal integer, temporal float, temporal text, temporal Boolean. Imagine, for example, that we want to describe the speed of a car. The speed changes over time, so a single speed value is not enough. Rather, we need a function from time to float. That would be temporal float. So computing the speed of a car would be temporal float. If we want to compute a predicate over a moving object, for example, saying that the car is close to the city center, this predicate will be sometimes true, sometimes false, according to the location, the changing location of the car. And then the result of such a predicate will be a temporal Boolean. So these types will support computing time-varying properties over the moving objects. So in short, MobilityDB provides these benefits. It has compact data storage for mobility data. It comes with a big number of functions to provide rich mobility analytics. It scales, it integrates with Citus in order to have cloud deployment. We will show this during the tutorial. It's easy to use because the query is in SQL. It's compatible with the PostgreSQL ecosystem because it's an extension, it's not a fork, and it's open source. So let's step back and speak about mobility data. How does mobility data look like? Mobility data come from many kinds of sensors. The most common one is GPS, or the Russian equivalent is a GLONASS, if I'm not mistaken. What you get from the GPS device will look more or less like this. You have a point and a timestamp, the two last columns in this table. And then you have a sequence of these. So according to the sampling rate, the frequency of taking observations of the sensor, you will get a location and a time. And you will also get some other event load according to the device. Maybe you get the signal quality, you get the speed of the movement, and any sensor more or less will give you this data, even if it is a AIS system for tracking ships or the radar system for tracking flights. You end up with a structure like this. And if we visualize this on a map, it's going to be discrete points like this. So every point is in a map, but the points are not connected together. But we know that the mobility in the physics, it's a continuous phenomena. And that's what mobility DB does. It puts back the continuity to the data. So it understands that these points, that the object didn't do jumps, the object rather went continuously, and it interpolates back between the points. So basically, the resolution of the sampling is set back to infinity, like how it is in the physical world. And there can be many ways to do this interpolation. In the simplest case, we do linear interpolation between every 2 points. We assume that the object has been going with the same speed in the same direction between 2 observations. But if we can do more sophisticated interpolation like map matching to really neatly put the object on the map, at the end, after ingesting the data in mobility DB, we know that the data will be represented in continuous way. While it looks like the data size will explode because we go to we interpolate, we go to infinite resolution, it's actually the opposite. Because when we do the interpolation, we can see that there are some points that are redundant in between that can be obtained from the interpolation that has been computed. Like this, we can get rid of many redundant observations between every 2 key observations where there is a change in a speed or a direction. Then we need to take an observation. Otherwise, we can interpolate between the points. So that comes to the compact representation that MobilityDB has for the mobility data. In practice, we have seen reduction in the size of data ranging from 10 times to 100 times. Even more important is that now in the database, you are storing complete movement trajectories rather than individual points. So in the table at the end, every row will be a complete movement, a trajectory of a vehicle. It will not be just a single point like the discrete representation, how it comes from the GPS device. And this leads to significant query speed up. You also have the interpolation. So now you can query the location and the properties of the object. Even at the time, there were no observation between 2 observations. Even if you don't have extra observations there, you can still query. And these types are provided as in the database. So you use them in your create table statements. And these types are supported with a big API of functions for data management. So that means significant reduction in the development time. You focus on doing the business logic, and then you push the mobility data management to the database through SQL. This is a nice example we always like to tell, especially in PGConf Russia, because it comes from Russia. So this was presented by Nina 2 years ago in the PostgreSQL conference, where a use case has been presented for the Moscow public transport, moving from the point-based representation, where you have a point and a timestamp to the left, to the mobility DB representation, where every row is a complete trajectory. If you can see well my screen, you will see that the object has point and then the @ symbol and then timestamp and another point at timestamp. So it's a compact representation of a complete trajectory, meaning that you move from an order of 10 billion rows, every row is a single point, into an order of thousands rows. So 15,000 rows in this case, because row will be a complete trajectory. A huge reduction in data size because of the normalization feature I mentioned, removing the redundant data. So from more than 500 megabytes per day and 300 gigabytes per year to only 5 megabytes per day and 2 gigabytes per year. So that's in terms of data migration and data size. In terms of functions, using the API, you can do aggregates. Here, for example, it's about computing the speed profile on a road segment and comparing different time instance, different snapshots in order to see whether the traffic improves or the other way around. Doing this for every road segment in a network, you end up with a velocity map like this, describing the traffic at a certain time frame in the city. There are also APIs for spatiotemporal proximity. These are have many applications. For example, this is real data from the Danish maritime. We see two real trajectories of ships, and in a database that have thousands of these, we want to check for near collision scenarios, whether two ships have been so close to each other risking a collision. And this can be expressed in MobilityDB in an SQL statement. This is a visualization of its results. We basically compute the time varying distance between the two objects, and once they become within a threshold of danger, we have this red alert until they separate back. And the idea, you do this query and you find the trajectories, the pairs that have this property. You give this to the port authorities, and they will see what are the reasons, how to avoid this, how to improve the security in the sea. The very same API, the very same function can be used in a completely different context. This is for COVID-19 contact tracing. Again, these are two real trajectories. We make a story about them, that the red guy is infected, has COVID, the blue one is not, and we want to see when they break the social distancing, 1.5 meters. And when this happens, we get this red alert. Well, just to be clear, visualization is created outside MobilityDB, but MobilityDB will help you to write a query to find which pairs of objects come close to each other. We are going to write a query like this today. Again, with the same API, it's not only the distance between two moving objects. We can measure the distance between a moving object and a static object. This is an example for a bus moving and bus coming close to advertising billboards. So the yellow dots are advertising billboards, and we want to assess the visibility of billboards. Because if we do this for every billboard and for every vehicle in the city, we know we can do pricing, better pricing for the advertising billboards, and we can plan better the advertising campaigns. So again, we want to see when a bus was close enough, say 30 meters to a billboard, it means that the billboard is visible to all the passengers in the vehicle. And if we do this for every vehicle, for every billboard, we can develop some price model. Besides the functions that MobilityDB implements directly, it also integrates with other tools, for example, to do map matching. You know that the signal you get from GPS typically has errors, so that if you plot it, it will be something like the left diagram. It will not be neatly on the street, but this can be corrected using a process called map matching, and put neatly on the street, which then will improve the accuracy of the analysis afterwards. So this, here we integrate with a tool called Barefoot, another open source, and clean the trajectories in Barefoot and consume them back in MobilityDB. In a similar way, MobilityDB integrates with ecosystem of PostgreSQL. It integrates with Citus for cloud deployment. We will see this today. It integrates with QGIS, for example, for visualization. That's how I created all the visualizations in this presentation. It has a Python driver. We have done some tests with PipelineDB to support streaming. Of course, it builds on top of PostGIS. By default, it will be compatible with other extensions. And then continuously, we are testing the integration with more and more extensions to see how compatible, how can we improve this integration. MobilityDB is an OSGeo project. To give a background, OSGeo is an open source geospatial foundation. That's the umbrella of the geospatial software. For example, it's the incubator of PostGIS, QGIS. So having MobilityDB in OSGeo is certifies that it's at high technical quality and it's usable and it's open source. We also in parallel work in making the standards. So the experience of MobilityDB, we try to standardize the data models and the functions built in MobilityDB. We try to push them for standardization in the Open Geospatial Consortium. And this comes to the distributed version of MobilityDB, but I will stop here. We start with the tutorial first, non-distributed, and then at the end of the tutorial, we will come to the distributed queries where MobilityDB integrates with Citus, and then I'll come back to this slide. So now to the action part. So you should have received this PDF. My colleagues sent it to the chat. Basically, we have prepared a MobilityDB server. Please try to connect to it, either from your PSQL or from pgadmin, would even be better if you have pgadmin, or whatever PostgreSQL client you have. So here is the IP, the username, and the database. Normally, you will not need the password, but we put it in case you are asked to provide it. Yeah. So in this database, it was created by a data generator that we have, the Berlin Mod benchmark, and I put the link here. So this database is available during the tutorial, but after the tutorial, if you see this video or if you want to do further tests, you can yourself generate the same data set using our data generator, and then try the queries in this document. The three tables we will be using during this tutorial. The first table called trips, and it has this structure. It has some identifier for the vehicle, for the day, for the sequence. So basically the scenario of this data that there are cars owned by people living in a city where a person will drive from home to work during the normal work hours in the morning, and then at the late afternoon, people will drive back from work to home, and then can also do some leisure trips in their neighborhood. This is all simulated with some random variables. and we generate a scenario of moving vehicles around it. So every vehicle will perform multiple trips in one day, and this is why we have a vehicle and the day and the sequence. So in one day, you have multiple trips will get different sequence, meaning that the three together are composite primary key. And then every trip will have a source and a target. These are nodes, identifiers for nodes, where it starts and where it ends. And we have the complete trip as a temporal geometry point. Yeah, so this is a complete trajectory. We will see how it looks like. So TGeom point, that's the mobility DB type. We also project to see the line string of the trip of type geometry. That's a post-GIS geometry. And this is a unique primary key constraint. There is also another table, municipalities. This is basically administrative regions in Brussels. The data happens in Brussels. It simulates the movement in Brussels. And what we care here in municipalities is the name of municipality and the geometry. So we will have queries to check the interaction between trips and municipalities. And there is another table, plan to OSM point. This comes from OpenStreetMaps data. And there we care about the name of the landmark and its geometry. Okay, so let's start with the first query. Let's just visualize how the data looks like. How does a trip attribute look like? How it is stored in the database. So let's do it together. We do select as text trip, and then we cast to varchar 100 in order to get a smaller string, because one trip is very long, can have 100 points. And we limit 5. Good. I'm zooming in. So you see here, this is what we saw in the slides. You see that we get an array of points with some coordinates at, and then a timestamp, and then another point and a timestamp, and so on. One trajectory can have hundreds or thousands of such points. And as explained, internally, MobilityDB will understand that there is interpolation between these points, and it will do linear interpolation. So we can query the location between the consecutive timestamps. Every line of these is a complete trip, a complete trajectory from start to end. If we want to access the individual points, this is a second query. We can call the function instance. That's a MobilityDB function. It will return an array of these components. And then we can do, this is a PostgreSQL array. We can do a nest and see. So we choose for a single trajectory and unnest all its points. So now we see more. We see that every point, every row is a point and a timestamp. So the point here is written in the well-known binary format because it's a post-GIS point. So this is a post-GIS display of the point and then a timestamp. And you see that the timestamp has a time zone. So if your mobility database happens in different cities with different time zones, they can all be integrated together in one database, and the time zone is taken care internally in the type representation. So like this, we basically have broken the trajectory again into the discrete representation where every row is a point. So I give some time that you try. And please ask if you feel you have questions. So let's see whether really someone is trying. Come on, we don't have many connections. So please connect and try.
Please tell us whether you have any problem in the connection. We can help you on that.
I'm giving some time because I know there is a lag between me speaking and you hearing because of the broadcasting and the streaming environment. Okay, now to the third query. Display the start and end timestamp of a trip. So we are going slowly over the API. So you know the functions that you can use to deal with the trip attribute. So there's a function called start timestamp that will get the very first timestamp of a trip. And another function end timestamp that will get the very last timestamp in a trip. So we can show this for every trajectory in the database. So we get something like this. So we see that the first trip starts in 1st of June 2020 at 9 a.m. So it looks like a trip, someone going to work. So going to work at 9 a.m. and then they arrive work at 9:46. So taking 3/4 an hour for the drive. And then the second trip is at 16:42. Again, this looks like someone going back from work to home to 17:23. A third trip at 21:25. So this looks like a leisure trip in the evening. It doesn't take too long. Yeah, again, these are all simulated trips using our data generator. So the key here is that you can access individual instance and properties about the moving object, the trip attribute. So I'll give 1 minute, you try. Okay, so we continue exploring the database we have. Now this query is, what is the time span of the whole data set? We have many trajectories in the database, and what is the very first time and the very last time in the whole data set? This is a simple aggregate over the previous query. So for every trip, we extract the start timestamp and the end timestamp, and then we aggregate min and max over all rows. So if we do it here, so you see that the earliest time stamp is 1st of June 2020 at 8 a.m. Someone going to work a bit early. And the latest one is 3rd of June after midnight. So 25 in the after midnight. So this looks like a trip that started in 2nd of June, just before midnight, and continued over until 3rd of June. It's basically in this data set that we have, we ran the simulator for 2 days to simulate trips for 2 days, 1st of June and 2nd of June. But what happens here is that there is a late leisure trip in the 2nd of June that continues over until 3rd of June. Take a minute to try. Okay, so now we want to see what is the driven distance of every trip. How many kilometers every trip was. So this is a function length. So you do a length of a temporal geometry point, and then you get the length in the units of the projection. If the projection is per meter, you get the number of meters, which is the case in the projection we use in this database. Or if the projection, the coordinate system is in feet, you get it like this. What you don't want to do is to call length for a geography object where the projection is latitude and longitude. In this case, you first need to change the projection and then call the length. So length has to get the object in some Cartesian coordinate system. And we will show later how to project the data to a different coordinate system. So in this case, the projection is metric. So after calling length, we divide by 1,000 in order to get in kilometers. And then we do this for every trip, limit 5. So we see that there is a quite varying trip distances. The one is 32 kilometers, 31 kilometers, 4 kilometers, and then even half kilometer, 3.5 kilometers. And that's a nice feature in this data generator, because it gives data with quite varying properties. So you can use it to test your hypothesis and the implementation of mobility functions. Okay, so where we are now. Some users. Good. So we have seen little by little some functions to get properties about the moving object. Now let's put many of them in one query and see some statistics for the data set. So here we again use the function length. And get aggregate over minimum. So what is the shortest trip? What is the longest trip? What is the average length of a trip? Here I didn't divide over 1,000, so the result will be in meters. And we see that the minimum length is almost half a kilometer, that the maximum length is almost 37.5 kilometers, and that the average length of a trip is about 15 kilometers. About the time, so there's a function duration that will give the time span of a trajectory. So we get the minimum duration, the maximum duration, and the average duration. Num instance will tell how many internal instances are there in the trip. And the idea here is to see how long the data representation is. And so we see the minimum number of instances, the maximum number of instances, the average. And most interestingly is the last one that we typically need in analyzing a mobility data set is to know the observation rate. How many instances per minute? So to know whether we have dense representation or rather sparse representation. So here we divide the number of instances over the number of seconds in the trip, over the time span of the trip, and then multiply by 60 to get the number of observations per minute. And here in this database, we have an average of 45 observations per minute, meaning that there is an observation every 1.3 seconds. That's quite dense, but this is simulated data. In reality, you normally will get every 10 seconds or more sparse. So take a minute to try yourself. So let's have a visual look of the data. We project the trip into a line string, a Postgres line string. This is a function trajectory. trajectory will take the spatiotemporal trip object and will remove the time dimension and will only provide the sequence of points with line segments in between. Represent this as a PostGIS line string. So if we do this for all trips, and if you have some tool to visualize like BGAdmin or better QGIS, let's have a look what we see. So in BGAdmin, for example, you will see a geometry object, and if you click the eye, you get a nice map view. So these are the projection of all the trips. And you see that Brussels have an outer ring, and there is an inner ring here, yet no car went here. So I'll show you in 2 queries how to see the map background. So if you have BGAdmin or if you are used to QGIS, try this query. Otherwise, what you will see is just the vehicle identifier and the line string object encoded in the well-known binary format. So we see that this trajectory function is a kind of casting because it takes the temporal geometry point object and outputs a PostGIS line string. But you can do better casting by simply cast to geometry. And in this case, why I say better, because instead of getting a line string, you get a line string M, and the M measure will contains the time. So here you see that every point will be longitude, latitude, an X and a Y, and then a time. And the time is encoded in epoch. These are the seconds since the January 1st, 1970. That's how the epoch is represented in PostGIS. And like this, well, some PostGIS users will call line string M a trajectory representation. So like this, you can port the data to PostGIS, including its time information. We use this often to create animations like the one in the slides. To convert to line string M, and then they take this data to QGIS and write some Python script to animate the points. Here's a ST as text function. That's a PostGIS function that displays a human readable text representation. So to convert the data, the display from well-known binary to well-known text. Okay, let's proceed. Now working with the projection of the data, we can first know what is the coordinate system of the temporal geometry point attribute by calling the function SRID. Here, this data is in some Belgian metric coordinate system 3857. And then we can transform to other coordinate systems using the function transform. It's a MobilityDB function, but internally it will call the ST transform of PostGIS to change the projection of the data. So here we change the projection from the from the 3857 into the 4326. This is a latitude and longitude. This is a geographic coordinate system. And display a snippet of the object as text. So now you see that the point coordinates changed into longitude and latitude. Still maintaining the time component. So this is still a MobilityDB temporal geometry object. We can try this transformation, for example, in this visualization query. So instead of visualizing the trip, we transform it, and then we will be able to see some background map for the data. Normally now it should show some background map from OSM. Because the background in PG admin is in 4326. I don't know why it doesn't show. Normally it should show. Maybe if we
maybe you can try with another window, a new window.
Let's first try a casting. Okay, this works. So you see Brussels in the background, and the trips go in the outer ring, some of them covering the inner ring. Okay, let's move forward. Yeah, now let's compute some time varying properties of the vehicle, for example, the speed. So as I explained in the slides, the speed of a vehicle is time varying. It changes over time. So by calling the speed operation, we get a temporal float. And now we are casting it to varchar 100 to see a snippet. So you see that we have the word stepwise. I'll explain what is it. And then we have some value 3. This is 3 meters per second at a certain timestamp. And then it moves to 5,5 at a second timestamp and so on. So we get a complete function, a continuous function from time to value. And this function is again interpolated. So 3,3 will be connected to 5,5. And we can query the speed at any intermediate time instant. And the way the data is interpolated here is stepwise, because so the function will be a step function. So the speed will be treated as constant between 2 time instants. And this comes from the linear interpolation. We assume that between 2 points, the movement has a constant speed. And then when we arrive to the second observation, it will have a constant speed to the third observation and so on. So the speed function is a step function in this case. So while in the previous query, we have been computing static properties of the trip, now we are computing dynamic properties that also change over time. So speed is 1. And we can further manipulate the temporal float type of the speed. For example, if we want to get the average speed over all time of the trip, then there is a function time-weighted average that will take a temporal float and summarize it into a single floating point number representing its average with time weighting. So here we multiply by 3.6 because the speed is computed meters per second. So we convert it to kilometers per hour. And if you do this query, you will see something like this. You will see that the first trip has an average speed of 42, almost 43 kilometers per hour, 46 kilometers per hour, 22 kilometers per hour, 18. So again, the data set has varying properties. Please try. And if you have any questions.
Just an aside comment with respect to the data generator. So this data is generated based on OpenStreetMaps. And in OpenStreetMaps, we have a maximal speed per route segment. So these trips satisfy the maximal speed in each route segment.
Let's move forward. So in this query, we want to compute the cumulative distance traveled by a vehicle as a temporal float. This is a cumulative distance is again time varying property. So the cumulative distance when the trip starts will be 0, and then it will be increasing over time. So after 5 seconds, it will have reached 100 meters. After 1 minute, it may have reached 1 kilometer, and so on. So the function cumulative distance will just produce will thus produce a temporal float, an increasing one. And the very last value of this temporal float, so if we say cumulative distance and then end value, the very last value should be the total length of the trip. And that's what we do in the third attribute here to validate. We compute the length of the trip. So let's do this query. Yeah, I have it here. So you see in the first attribute, we get a temporal float. We display it as a varchar. And then the last value of the cumulative length is the same as the total length. So the benefit is when you have the cumulative length function, you can query at any time what was the distance already driven by the vehicle until this moment. Questions?
For the moment, I don't see many questions in the chat.
Yeah, maybe these following queries are more interesting. So we are again going little by little over the API. The API is more functions than this, but we give you an entry to using MobilityDB. So in this query, we want to see which trips passed the municipality of Evere. So Evere is a region in Brussels, and we want to see which trips during their driving crossed or entered Evere. And in this case, a function is intersects. It's a MobilityDB function that will take a temporal point and the geometry, and will tell whether they have ever intersected. So if the trip has ever intersected the geometry of the municipality, Evere, it will be reported. So here we filter for Evere, and then we join the two tables based on their intersection. So we see that there are in total 6 trips, mostly coming from vehicle 18 and vehicle 17. So these trips either have home or work, probably in Evere. And it can be interesting to see the plan of this query. So you see in the plan that there is an index scan for the trips SPGIST index on the trip attribute. So MobilityDB extends GIST and SPGIST indexes for the temporal geometry attributes. Basically, every trip is summarized into a 3D box. 3D because 2Ds are for the spatial and the third dimension for time. So there's one box per temporal geometry point, and these boxes are organized in an R3 implementation of the gist, or in an space partitioning tree, octet tree for the SP gist. They are organized in a balanced tree structure that will then be used to do spatial or temporal or spatiotemporal intersection queries. So in this case, because the other operand of the intersects is a geometry, it's going to overlap the box of the trip with the box of the geometry. The box of the trip is 3D. The box of the geometry is only 2D, so it will overlap the common dimensions. And by this, it will do a quick filtering on the index, and only these who satisfy the filter will go for the exact evaluation of the predicate. Let's move to more analytical queries. So combining functions in the API to do deeper analysis for the data. Here we want to see what was the closest distance between a vehicle and some point of interest. Grande Place, this is a key sightseeing in Brussels. So what was the closest distance between any vehicle and Grande Place? For this query, we join the table trips with the table Planet OSM point. We filter the points of interest for the Grande Place. And then here, what we do is we compute the shortest distance between every trip and way and the geometry of the Grande Place. So this operation will compute the closest point of approach, the shortest distance ever between a trip and the point. And then we will do a minimum aggregate over all trips. In this case, the minimum distance that a trip had to Grande Place was 1 kilometer and 200 meters. In the next query, how many trips start and finish in different municipalities? So to do this query, we join the trips with the municipalities table twice. And the joining condition is that the start value of the trip will intersect one municipality, and the end value of the trip will do ST intersects the second municipality, and then the two municipalities are not the same. We see that we have 38 of these trips. I'll move a bit quickly to cover all the queries. Here we want to do an analysis for accidents. Are there car accidents in this database? Yeah. So we want to see whether two cars came very close to one another, so an accident or a danger of accident. That's very much similar to the query I showed the visualization in the slides. Here, where we wanted to see when two ships approach each other in a near collision scenario. So the way to do it here. So we join the trips table with itself. It's a self join. And then we check that it's a different vehicle. So we don't join the same trip with itself. And the key operation here is TD within. It reads temporal distance within. So we want to check for pairs of trips that have ever been within 10 meters distance to each other. Yeah. So TD within will return a temporal Boolean. Whenever the two objects are apart, we have a false. And if they come close, we have a true. And if they come apart again, we have false. So the result of TD within is a temporal Boolean. And this operation, it reads ever equal true. So whether this temporal Boolean has, for at least for a single time instant, have been true. In this case, we want to return these two vehicles. So happily, there are no such near collision. So we get an empty result. Another query, what is the average duration of trips that start in the municipality of Oakle? Okay, I think you will be able to do this query. Basically, we filter, we join the trips with the municipalities, and we filter for the municipality of Oakle. And then we see that the start value of the trip, the very first point in the trip, intersects the geometry of Oakle. And if this is the case, then we compute the duration of the trip, and we take a global average for all trips that start in Oakle. So here we see that this average is 42 minutes. Okay, now we are coming to another part of MobilityDB, the distributed MobilityDB. That's where MobilityDB is put in a cluster with the help of Citus. So the configuration is as such. So in the cluster, there will be one node as coordinator. This node will have PostgreSQL, PostGIS, MobilityDB, and Citus. And there will be many workers. Again, if each of them has the same stack, PostgreSQL, PostGIS, MobilityDB, and Citus. And we come to the big table, which is the trips. Normally, in this case, will be the trips table. We call the Citus function create distributed table. It's going to shard the table into multiple partitions, do hash sharding based on the key. And for the tables that we want to replicate at the workers, we create reference table. So in our case, we shard the trips table and we replicate the municipalities table. So like this, every worker will have a piece, a single shard could be multiple shards of the trips table, and we'll have a complete copy of the municipalities table. Yeah. And then we can create indexes that will also be distributed and so on. Then the user query remains the same. We write the same SQL, and it will be the distributed planner of Cytus who will take care to distribute the query. And the MobilityDB functions are built in a way that they will be able, that Cytus will seamlessly, without knowing these functions, will distribute the execution of them. Well, for most of the query types, there are few query types that cannot be distributed, but this is a detail we don't have. It's not time to mention these details. Okay, so let's try. What is the total driven distance by all vehicles in the municipality of Anderlecht? So we want to see how long the vehicles have been inside the municipality of Anderlecht. To do this, we take every trip, we restrict it to the geometry of Anderlecht. So we cut the trip. So the trip, for example, comes from outside Anderlecht, enters and exits. So we will cut only the piece that is inside Anderlecht by the add geometry operation. So we get a sub-trajectory. And then for this sub-trajectory, compute the length, divide the length over 1,000 to get a kilometer, and then do the sum over all. Of course, joining the trips table with the municipalities and filtering for Anderlecht. This one is for index access to see which trips overlap the box of Anderlecht. So this is to make the query more efficient. But you see here that we are not querying the table trips. We are rather querying the trips _d. This is the distributed version of the trips. And we are querying the municipalities R. This is the replicated version of the municipalities. So if we run this query, here, this query will not run on a single node, it will run on a cluster that we have also prepared. It's in your connection already. So you see its result. Let's look at the explain, or we write explain ourselves to see the plan. So you see here, most important is that there is a custom scan of Cytus adaptive, that's the query executor of Cytus. So Cytus basically creates 32 tasks, distributes them over the workers. In this case, we have 2 workers. Each of them will get 16 tasks. And every task will will basically do the query filtering for Anderlecht, and then intersecting with the add geometry operation and compute this aggregate within the shard that it has. So you see from the plan that this query has been already distributed over the cluster. Next query is gives a number of the trips such that their route intersects the municipality of Jet for more than 10 minutes. So here again, we do the add geometry. we see we cut the part of the trip that is inside the municipality of Jet, but we care about the duration of this part if it is more than 10 minutes. Yeah. So again, this query is issued to the distributed version of trips and the replicated version of municipalities. And it gives 2. No, not this one. The broadcasting environment is making my browser very heavy. So it's not really responding quickly. So again, this query is issued to the small cluster we have. And we get result 2. So I remember numbers that the previous query, for example, if issued to a single node, it took about 8 seconds, and when issued to the cluster, of course, it's much faster. It took 1.5 seconds. Now, the last query in this tutorial is more analytical. For every speed range of 20, give the total distance traveled by all vehicles within that range. So to understand, let's look at the result. We want to see what was the total distance for all vehicles driving from 0 to 20 kilometers per hour, and the distance driven at the speed of 20 to 40 kilometers per hour, and so on. So for every slice of 20 kilometers per hour, we want to see the driven distance. For example, here we see that there is a higher concentration for the distance between 40 and 60, for the speed between 40 and 60, but still there is some cars speed up. We have 200 kilometers driven at a very high speed. So the query will create the ranges, 0 to 20, 20 to 40, and so on. And then we'll compute the speed of the trip and will restrict the speed to this range. So the speed is a temporal float, and when we restrict it to a certain value range, we also end up with a temporal float, but it will has gaps in the middle. And then here we get the time and compute the and restrict the trip to these time intervals, and then compute the total length. It's a bit complex, so if you have questions here, please tell.
What is important to understand here is the float range is a PostgreSQL range type. So we are fully integrated with PostgreSQL types, including range types.
Yeah, so this brings us to the closing of the tutorial. You have questions of kind of usage questions, please subscribe to this mailing list and send to us there. If you are interested about how MobilityDB is developed and you have comments and suggestions, please go to the MobilityDB developer mailing lists. And also in the slides, you will have links for the GitHub of MobilityDB, the source, the manual that describes the API we have been using and the rest of API. As mentioned, MobilityDB has almost 300 functions. There is a Docker container for a quick start. This is a data generator that has been used to generate the data for this tutorial. There is a MobilityDB workshop I go here and show you what it has. So it has many examples for applying MobilityDB in real scenarios. The first workshop is for analyzing ship data, real ship trajectories. So it will tell you where to download the data and how to put it in MobilityDB, how to analyze it, and so on. Second one is for analyzing GTFS data, the public transport schedules. Third workshop is about analyzing Google location history. You know, you can download, if you navigate with Google Maps, you can download your trajectories, the historical ones, and then you can load them in MobilityDB and process them. And in general, if you have GPS trajectories in comma-separated format, this workshop will tell you how to load the data and to query it. There is a Python driver providing database connectivity and providing the MobilityDB types in Python environment. And science behind MobilityDB, there's a list of our published papers. Good, so we are done with the tutorial. You are welcome to ask your questions. And thank you for listening.
Thank you for listening.
When we talk about linear interpolation, what kind of lines we mean? Straight or geodetic?
Both are possible, depending of whether your underlying time is geometry or geography from Postgres. And so we have both tgeom type for underlying geometries and tgeog type for underlying geographies. And so we basically delegate this calculation to PostGIS.
Okay, thanks. And second question is about border of spherical coordinates somewhere in Japan, I suppose, or ocean. Is it how MobilityDB handles it when we cross it?
Very good question indeed. But we have the underlying philosophy of MobilityDB is that we take care of the temporal aspects and delegates all the geographic information calculations to Postgres. So basically, Postgres is the expert extension for dealing with data. We send the query to Postgres, we get the results, and we format it into the temporal perspective.
That's good. That's good. And maybe last question from me is about something roadmap. Do you have anything on roadmap, some common features or some interesting releases?
I didn't understand very well this question. Could you please repeat it?
Yeah. The question is about roadmap of MobilityDB. Do you have anything coming in near releases, or maybe some huge feature which will be attractive for many companies?
But what do you mean by roadmaps? For example, in this particular tutorial, we have imported the OSM underlying roadmap. We defined it for Brussels, but you can import, for example, your underlying roadmap from.
No, that's not a question, Esteban. Sorry for interrupting you. He's asking about the future plan for MobilityDB.
A roadmap. Okay, so thank you.
Sorry for my English.
No, don't worry.
That's correct.
So, yes, thank you. When we are exploring many possible things, for example, one of the current issues that we are exploring is visualization. Visualization is a complex issue because putting thousands or 2,000 vehicles to animate in real time, it's complex, so we are working on that. Other issues we are working on real time, working on Java connectivity, Java JDBC driver. We have working on trajectory segmentation, trajectory simplification. So we are exploring through multiple master theses, PhD theses. One important one, we continue working with Citus in supporting more and more distributed queries. This is one current PhD thesis we are working on. Another very important one is this tutorial have only shown moving points, but we have already another current PhD thesis working on moving geometries, and this is important. For example, in the case of autonomous vehicles, you have your latitude and longitude, but you need to have explicitly the 3D size of the vehicle, of the full geometry moving, to understand whether two cars will collide or not, or are close to another. So we are exploring multiple perspectives through papers, master theses, PhD tests.